Okay, so 102 wants to find the linear approximation of the function square root of 25 minus x squared near, what was it, x equals 3. So, in other words, if you have 25 minus x squared, if you didn't know, if you take the square root of 25 minus x squared, it's going to look like half a circle, yes? So that thing's going to look like half a circle, and it's going to go rip, where over here is positive 5, and over here this is negative 5. That's what the square root of 25 minus x squared is going to look like. And so we're saying over here at 3, I want you to find that a linear approximation. In other words, find me that tangent line at x is equal to 3. And trust me, it's touching. So I can do this. Grab it, move it. Oh, poop on a poop. Just these. You let me do just this. No, just this. Well, let me move just this. Yes. Okay, there. Okay. So we're wanting to find that equation of that red tangent line. And we know that a function at a is equal to 3, so that's a constant, would just be f at a plus, so a place to start, plus how does the function change and over what interval? So that's like your delta x, and that's your derivative, right? So f at a, in this case, f at 3 is equal to the square root of 25 minus 3 squared. So that's going to be 25 minus 9, which is square root of 16, yes, which is 4. So that means this is 4 plus, we now need to find the derivative. Let me move this over here. So the derivative is just going to be, well, this is 25 minus x squared to the 1/2. So its derivative is half 25 minus x squared to the negative 1/2. And then you have to do the chain rule, and a negative 2x pops out. So that's going to be negative x over the square root of 25 minus x squared, yes? So the derivative at 3 is going to end up being negative 3 over square root of 25 minus 3 squared. So it's going to be negative 3/4, right? So now if you take this value, so that derivative at a is just equal to negative 3/4, and that f of 3 is just equal to 4. So if we're centered at 3, the derivative at 3 is negative 3/4, and this is x minus 3, right? X minus 3. So that's what that thing's going to turn out to be. And there you go. That is our linear approximation. Everything in here, okay? So it's just 4 minus 3/4 x minus 3. That's where our linear approximation is. So now let's look at, what do we want? 103. And so now when we're looking at 103, again, it wants us to find the linearization of f of x is equal to the cube root of 1 plus 3x at a equals 0, and state the corresponding linear approximation and use it to give an appropriate value for the cube root at 1.03. So let's first find the linear approximation. We know it's the point plus the derivative at a point, x minus the point. In this case, our point's 0. So it's really f at 0 plus the derivative at 0, x minus 0, right? But f of 0 is just equal to cube root of 1 plus 3 times 0, which is the cube root of 1, which is 1. So this is just 1, because I found f of 0 to be 1 over here, right? You move this stuff over here. Also, you find that the derivative, because this is just stuff to the 1/3, this derivative is 1/3 stuff to the -2/3, but you have to do the chain rule, and you end up getting a 3 that pops out. So this should just be 1 over 1 plus 3x to the 2/3, right? Okay. So if that's the case, so the derivative at 0 is just going to end up being 1, right? 1 over 1 plus 3, 0, all that stuff to the 2/3 is just 1. So the derivative at 0 is 1. So that means I can take this and plug in something. So that's plus 1 times, and this is just going to end up being x. So it's 1 plus x. All right. Linearization is 1 plus x. And it wants us to use that to figure out what's going on. So find prox for the cube root of 1.03. But guess what? That's exactly equal to the cube root of 1 plus 3 times 0.01. Do you see how now we have rewritten what we want, cube root of 1.03, as 1 plus 3 times something? And why is that important? Because remember, our function was the cube root of 1 plus 3 times something. And so that means our approximation is going to be 1 plus this value right here, 0.01. So my approximation is 1.01. Make sense? So we took what we want and changed the form into 1 plus 3 times something, because that was our original function that we got an approximation for, 1 plus 3 times something, that cube root of. Okay? Great work. Last one we have is 104. So if we go back to 104, we are so close to being done. 104, it just says evaluate dy. So it says find dy if y is equal to x cubed minus 2x squared plus 1, x equals 2, and dx is equal to 0.02. So don't forget dy is just equal to the derivative times dx. You know that because dy over dx is equal to derivative. But the derivative of this thing up here is just 3x squared minus 4x. And then dx, right? But if x is equal to 2, that means I have 3 times 2, take this 2 squared, minus 4 times 2, but then dx is equal to 0.02. That means this dx is equal to 0.02. And so you end up multiplying all that together, and you get that dy is equal to 0.8. Yay. And just a reminder, if we're looking at any sort of a function value like this, and visually we have the tangent line, just to remind us what's going on here. Let's say that this is x, and this is x plus a little bit. So maybe we call this centered at A. No, that's fine, that's fine. This is x, and this is x plus a little bit. Remember that this right here, this height is delta y. That's how y is changing over the interval, and this is how x is changing over the interval. Don't forget, delta x is exactly the same as dx, yes? But delta y is over your interval, not how. Dy is how is the tangent line rising or falling, so that is dy. How is the function rising or falling? This right here, that's delta y. So how's the function rising or falling over this interval? That's delta y. How is the tangent line rising or falling? That's dy. We're done. Peace out.